Okay, so now we're going to be talking about the electric field within a sphere of non-uniform charge density. So what that's going to look like is we have our sphere. I already drew it because all these little pieces of charge take a really long time to draw. So we have our sphere with a radius of big R, and then we have our Gaussian surface within that sphere, and that's with radius of little r. Now, as you can see, everywhere on the sphere, the electric field makes a flux angle, or makes an angle of 0 with the flux, dA, represented by this little blue arrow right here. So that means that it's going to be cosine of 0 when we do our Gauss's law equations. Okay, so when you're given a problem where you have the electric field within a sphere of non-uniform charge density, they're always going to give you an equation to describe that charge density. So in this case, say that our equation was, say that it was that rho equals C times R. And it's okay that this is the little r because it's saying that for every amount of radius that you go out, the charge is going to increase by C. C is just some constant. You don't need to worry about solving for it. Alright, so, and as we learned before when we were dealing with our infinite line of charge and our and the electric field enclosed within a sphere, rho equals the charge per unit volume, but in differential form, it's differential units of charge, so infinitely small pieces of charge per infinitely small units of volume. And like we did with our other density equations, you can manipulate this to solve for Q or V or dQ or dV. You can do it whatever you need to do with it. Alright, so another way to write volume is surface area times the radius. And we're going to do that, but we're going to do that in differential form because we have our volume in differential form. So differential volume equals surface area of that sphere times the differential units of radius. Alright, now we can get to work with Gauss' law. Oh, not quite yet, actually. Alright, so now we can manipulate this equation to be dq equals rho dv. Right? And so now to sub in for this dv, which we just solved for, we can say that dq equals rho times the surface area times dr, and that's, yep, pdv. Okay. Now, we're going to sub in for two things. dq equals rho, but rho, like they gave us in the problem, is C times R, times the surface area, and the surface area of a sphere is 4 pi r squared. So, let's see. Okay, it's recording. And this, okay, so the surface area is 4 pi r squared, and then dr is just dr. And this is good. This is the form that we need it in because the only variables we have are r's. C is a constant, and 4 pi is also a constant, so that's good. And we can combine our like terms, our r's, so that dq equals CR cubed times 4 pi dr. Alright, so that's dq. And now we can use our Gauss's law and solve for the electric field. So, let's see. So we have the electric field times cosine of 0, which is 1. So the electric field times 1 times the closed integral of the surface area, or the closed integral of area, which is the surface area, equals 4 pi c times the integral of r cubed dr. I'll make that a little bit bigger. Alright, so all I did was I just rearranged this equation. I pulled all my constants out, which were 4, pi, and c, and so that way I'm only left integrating r cubed times, with respect to the radius. Now our bounds are very, very important. So as you can see here, we're only looking for the charge in this, within this Gaussian surface. So you want to integrate with respect to the radius from the center, which would be at 0, to this ending point, which is r, 0 to r. 0 to r. And of course, as we see up here, that's the total charge enclosed, and we need to divide it by epsilon naught. And now comes the fun part. We can cancel some stuff out after we sub in for df. So e, I'm just going to get rid of that 1. We know that anything multiplied by 1 is itself. E times 4 pi r squared equals c times 4 pi. And then this is, after we integrate this, we get r to the 4th over 4. I'll just rewrite that bracket. R to the 4th over 4. So c times 4 pi r to the 4th over 4 epsilon naught. And now we can cancel some stuff out. So we have 4 on both sides, that's gone. We have pi on both sides, that's gone. We have r squared and r to the 4th, so this is gone, and this is r to the 2nd over 4 epsilon naught. So we ultimately end up with the electric field as being c r squared over 4 epsilon naught. And this is the electric field due to a sphere of non-uniform charge density, and you're trying to find the electric field within that sphere. Okay, there are a couple other important things to remember with Gauss's law. One of them I mentioned throughout this tutorial is that conductors do not have an electric field within them. And I will show you why in 1 second. Oh, this marker's dead. Okay. So if you have, let's say that you have a sphere. No more math. Don't worry. No more math. If you have a sphere that looks like this, and you're trying to put an electric field through it, and this is, we'll say that this is made out of some kind of conducting metal. You're sending an electric field, and as we know, electric fields begin on positive field lines and terminate on negative charges. So we also know that like charges repel and opposite charges attract. And since this is a conductor, and the electrons and charges easily set themselves up in ways that obey those laws, we're going to get a lot of negative charges on this side. Well, we'll get 4 negative charges on this side, so we have 4 positive charges. And field lines start on positive charges and they terminate on negative charges. So as soon as this field line hits that negative charge, it's going to stop. Right? Now, this is a neutral sphere, metal conducting sphere. So for every one of these negative charges, it must have a positive charge. And these positive charges show up as far away from these ones as they can, because like charges repel. So you end up with 4 positive charges to balance out these 4 negative charges, which have balanced out these 4 positive charges. And like I said before, field lines start on positive charges, so they're going to resume over here on these positive charges. Okay, but inside, there's no electric field. And that's why if you're in a car and you get struck, and your car gets struck by lightning, you're not going to get hurt. You're encased in this metal car, which acts like a sphere. And this whole phenomenon is called Gaussian shielding. Okay, let's see. The other important thing to remember is that when you have an insulator, the charge will reside on the inside, so this thing doesn't happen with insulators. That's why there's a common myth that the reason why cars protect you so well from lightning storms is because of their rubber tires. That's not true. That's like saying that an umbrella protects you from a tsunami. It doesn't make any sense. Okay, if you have a sphere with uniform or non-uniform charge density, and you're asked to find the electric field on a point outside of that sphere, so say that this is your sphere, and this is R. Let me write that a little bigger. And say that the distance from the center to the outside is capital R. And the problem asks you for what the electric field would be if little r is greater than big R. So that means that little r is somewhere out here. In that case, you can just treat this sphere like a point charge because the radius that you're looking at it from is beyond the outside point. If a problem asks you where the electric field would be when little r equals big R, you just do your equations exactly like we did them, but you just plug in for big R, and sometimes that allows you to cancel stuff out. Sometimes it doesn't. Just do the equations the way that we talked about, and you'll be fine. All right, so I think that's about it for Gauss's law. Hopefully that helped a little bit. Yeah, good luck with physics.